We want to say just a few words about the solid Earth, and in particular the solid Earth as it pertains to climate and weather. The two things I want to make sure you know about are plate tectonics, there it goes, and continental drift, and they kind of are the same thing. They go hand in hand with each other. Let's have a quick look at a diagram here that I stole off the internet. Here's a cross section through the Earth. Okay, let's get the pen going. What color? Let's go blue. All right. Right around along here, if you can see the blue line, is the surface of the Earth. So above this blue line is the atmosphere, and the atmosphere consists of layers: the troposphere, where we live, the stratosphere, the ozone layer, the mesosphere, and the thermosphere, and eventually outer space. And oh, here's one of the shuttles. So this must be an old picture because the fleet's not flying anymore. And then back below the surface is the solid Earth. And what we care about is that there's a liquid core, and then you've got the mantle, and on top of the mantle you've got the crust, which has varying thicknesses. Okay, it's, oh sorry, hand slipped, it's this light brown stuff, the crust of the Earth. Okay, and something like about 100 years ago somebody figured out that the crust isn't stationary, but instead there are lumps of crust that are moving around. And basically what's happening is that because the core is hot, there are convection currents inside the planet Earth, and those convection currents cause pieces of crust to move around, and they either spread apart from each other or they converge and form mountain ranges. So that is the idea of plate tectonics, or that is the idea of continental drift. And we've got a movie here. Okay, here's the website, ucmp.berkeley.edu, and so on and so forth. This shows the motion of continents over the past several 100 million years. And it goes by rather fast, so let me expando, and then we can just keep going. So let's see, what have we got here? This counter in the bottom right is the number of million years ago. So it begins 700 million years ago, and it ends now. And the red arrow going up and down the side shows you where you are. Let's see if I can persuade this to do something interesting. All right, about just a little over 200 million years ago, all of the continents were clumped together in one super landmass called Pangaea, and after that they moved apart so that you end up with what we have now: Africa, South America, North America, Australia, India, Eurasia. If we go back to about 200 million years ago, you can see that they're all together. And if I can just start this, here you are 100 million years ago, South America and Africa separating. That thing there, that's India heading towards Eurasia. And the point is this doesn't really matter for today's weather, but 60 million years ago the continental separations were quite different from what they are now. Well, somewhat different from what they are now, and so that would have changed the climate. For example, there was an open gap in here between North and South America, so there would have been an ocean flow between these two regions, and the distance between South America and Africa was much narrower, so you might have had more intense ocean currents in this region, and it would have had a big impact on climate. And there is no Himalayas or Tibet yet. That happens as India approaches the mainland, and the crushing action causes the Tibetan plateau, which has a big influence on global climate. So for people who are interested in what climate was like, they like to look at the former arrangements of the land masses. Well, it becomes an important factor. One more time. And there you go. The other thing that we're interested in is this. Okay, and whoops, let's get rid of that. What we're interested here is what happens when some of this this crust moving around the surface of the planet, when two pieces of crust collide. Then you get a process known as subduction. And what you can see here in this diagram, which is just a random diagram I got off the web, what you can see here is that this oceanic crust, shown in the light blue, this piece of crust is colliding with another piece of crust, and this piece of crust is being subducted, which means that it is diving deep under this piece of crust over here. And what matters here is that whatever is on the ocean floor is subducted deep into the core of the planet and basically lost for a long time. This matters to us, as we will see quite shortly, in the carbon cycle. If there is any, that didn't work. Okay, if there's any carbon that's part of the oceanic crust, it gets subducted deep into the core of the planet and plays no role in the ocean, the atmosphere, the biosphere for millions of years. So going back to our PowerPoint slides then, plate tectonics and continental drift play a role in climate and in climate change. It's very important to recognize that climate change has been happening for millions of years, so there's no reason to expect that our climate is not going to continue to change. Plate tectonics gives rise to what I just talked about in this diagram here of sequestration of carbon deep into the solid earth. And so the whole thing does have a role in climate.